industry. Overall, there are two carbon capturing methods in concrete. One is a physical approach by entrapping the CO2 molecules inside the microstructure of the recycled aggregate. And the other one is the chemical approach, which actually breaks the bonds between oxygen and carbon, and as a result has a higher absorption rate. I'll try to use minimum amount of technical terms just to make the understanding easier for you. But if you're interested in knowing more about these techniques, feel free to contact me in person and we can have a chat about these later on. The laboratory results will be shared with you in the following that give you a deep insight about the applicability of these techniques. The research future plan will also let you know about the direction of this research. So, as a history and a context, the graph that you're watching now is a representation of Australian population growth. And as you can see, since 1960, for a 50-year span, the population had doubled from almost 10 million people to now more than 20 million people. This simply means that there are more people looking for housing in Australia, which itself indicates the need for more construction and materials. Just as something to complete this graph, NSW had recorded the highest growth amongst other states, following by Victoria and Queensland. The government had also have comprehensive plans to address the future needs precisely in an environmental manner by using less harmful practices. Further on, we will review a few of the relevant states' legislation and active entities in this field, particularly in a wider national scale. As mentioned, higher population leads to a higher demand for housing and construction. Concrete, as the most dominant material in terms of consumption in the building sector, secures the second place as the most widely used material around the world after water. Cement, aggregate, and water, plus some additives, are the basic ingredients of this material, as you know. So if we're about to do something about the concrete carbon footprint, the logical approach that is to find the traces of emission in its component being cement or aggregate, assuming that water does not have any environmental impact. During the research that we have conducted with Kanmani Tekendron, who she is attending at the moment, and this is great to have her around. The focus was mostly placed on the aggregate and the ways in which this material could become more environmental throughout the recycling process. The cement portion of the mix, however, can also be modified in terms of carbon emission, but that's a difficult topic. That's a difficult and also different topic, which is not in the scope of this current research. A few notes before we dive into the so-called technologies or in the technical aspect of the research. For each ton of concrete that is produced, 1 ton of CO2 emits in the atmosphere, and councils in NSW are now implementing life cycle analysis for building projects, which means that they will get certified for green building ratings, and that ultimately can reduce the amount of tax that the construction entities are about to pay. Green Building Council of Australia is an NGO that is regulating the new environmental laws, but they have a long way to go because in practice, there are still people that are sticking with those traditional methods that we're using. Other countries such as UK had embraced the concept of zero carbon building design in their practices. So as said, this table shows the entities that are actively regulating the environmental legislations in Australia nationwide. New South Wales, compared to the other states, has the most mature way of implementing those legislations. But as you can see, there are only road regulatory bodies that are implementing the use of recycled aggregate. They're specifying some sort of a standard codes for the use of recycled aggregate as the base, as a road-based material. Um, Northern Territory still missing, but it has a lot of opportunity for itself in the future to implement those legislations. Um, so let's move on to this CO2 capturing technique and in the history of the CO2 capturing technique um, in Australia. CSIRO, that's Commonwealth Science and Research Organization, had invested about $1 billion so far on CO2 capturing technologies, in collaboration with Japanese partners since a couple of years ago. I believe that the project has started in 2011 and left unattended almost by 2018 and 2019, but the latest updates were that they are still pushing forward to get back on the track to implement these CO2 capturing technologies, particularly in the energy sector, where the coal is being burned for energy production and generation. But in construction, there are less than a handful of research projects, and this current research that you're following now is just one of those. The CO2 capturing techniques, as it is implemented in the coal power plants, has three different, let's say, approaches. Post-combustion, pre-combustion, and oxy-fuel combustion are those three technologies for CO2 capturing techniques. Post-combustion, where CO2 is being absorbed or captured after the coal is burned. Pre-combustion is retracting of CO2 gas before the coal enters the boiler. So that boiler is where the coal is being burned and water will be boiled and causes the turbine to rotate and generate the energy. So in the pre-combustion, what basically happens is that they're chemically treating the coal, and that causes the flue gas to be free of CO2. Oxy-fuel combustion had shown promising results on paper, but had never turned into reality. And because of that, we will leave it as it is. The technique that is applicable in the construction industry for us is the post-combustion, because we want to actually do something with the CO2 gas. We do not want to prevent um, the emission of CO2 gas. We want to entrap the CO2 gas. We want to break the bondings between carbon and oxygen in order to make it a less harmful substance to the environment. So we'll be mostly focusing on post-combustion. And as you can see here is the schema, the process that post-combustion takes in order to absorb the CO2. So what we need to know, what we took from this post-combustion capture is mostly for this tower. This tower that says CO2 absorber is basically a fountain of a chemical substance. That CO2 gas is being exposed to that substance and then being chemically activated or turned into some other useful substances as a result later on in the process. So how is it applicable in the construction industry and particularly in concrete production? There are two ways that these CO2, are actually more than two ways to implement the CO2 capturing techniques. But in concrete production, we can either play around with cement production or the use of recycled aggregate. But of course, you can say that steel manufacturing also contributes a lot to the CO2, the global CO2 emission. But we will be mostly focusing on recycled aggregate throughout this research. The first method that we've used in 2018, and actually, if you want to get more into details about this physical approach, you can just type in into scientific databases, look for CO2 concrete, and you'll get a lot of results about this particular method. The physical approach that was introduced is in fact deployed by the exposure of recycled aggregate in the pressurized CO2 chamber. This giant metal container that you see is actually a pressure vessel. This is all can be found under the term of CO2 concrete in the scientific literature if you're interested into doing more research on your own. Before 2018 in Sydney, there was only a chamber with 50 kilogram carbonation capacity. You can actually find this behind this picture, that cubic pressure vessel is that 50 kilogram um, pressure vessel. Our research team had made an effort to design and manufacture and upscale the chamber with the capacity of 1 ton carbonation per hour. The picture on the left is the picture of the new chamber, and the picture on the right is our design for deformation of the steel shell, which is limited to 6 millimeter on each side based on the recommendation of AS 1210 for pressure vessels. The chamber can easily take up to 700 kilopascal of gas pressure inside. The physical process is as simple as this. So you pour the recycled aggregate inside this container, inside this chamber, close the cap and seal it, and then introduce the pressurized CO2 via the allocated nozzles for a certain period of time. And your carbonized aggregate is ready after, say, 1 or 2 hours. How effective this method is a question that came into mind before we get into the chemical approach. The fact is that most of the injected gas immediately escapes as soon as you unseal the cap. It is claimed that 10% of the injected gas is absorbed by the aggregate. And the fact is that the bond energy between oxygen and carbon within the molecules of the carbon dioxide is so high that a low 150 kilopascal cannot simply break this covalent bond. That 10% absorption is most likely happen due to the hydration reaction and the physical entrapment of CO2 gas inside the microstructure of the aggregates. These are the results that we got from mixing physically carbon conditioned recycled aggregate in concrete. These colorful aggregates that you see are actually the recycled aggregate. When you compare it with the control sample at the age of 28 days, you can see that we have a slight increase in the compressive strength and a considerable drop in the slump, which makes it a bit harder to work with. And the permeability is also higher in carbon condition, or say a concrete that uses recycled aggregates as a portion of it. These aggregates contain brick, which has a higher porosity, and thus the water absorption is usually higher. So everything that said before had led us to the chemical approach. In 2019, after observing the low absorption rate by the physical approach, that was a 10% CO2 absorption, we came up with a new chemical approach. The claim here is more than 90% absorption rate. And as you can see, we had also solved the workability issue on the right-hand side picture in a way that recycled concrete is now flowable in a degree comparable with self-compacting concrete. So the typical slump test is not applicable in this type of concrete, and we have to work with the flow table. This steel pan that you see is actually the flow table. You will allow the concrete to expand in diameter in either ways. The way, actually, let me say that we made this chemical liquid substance and then added to the concrete mix, which caused this shape and the results that you will see later on. That chemical substance refers to the post-combustion technique that was discussed in a couple of slides ago. If you remember, the post-combustion techniques in coal power plants, the CO2 absorber tower is actually a fountain for a substance called monoethanol amine. So that's an alcohol plus an amine-based substance, or we can abbreviate that to MEA. What we did was to mix the MEA with the so-called polycarboxylic superplasticizer in a preliminary study. We then injected the CO2 gas in the mix and capped the container for 24 hours. We do not know the exact chemical product characterization yet, but what is apparent is that the resulting substance has a high basic behavior and that the reaction is an exothermic one, i.e., it radiates heat upon the development. Also, the pressure inside the container had dropped dramatically in the first 30 hours of development. The, the development of the chemical reaction, which itself indicates that the gas pressure had disappeared, or you can say that the CO2 molecules was decomposed. Um, Now that we can compare the physical approach with the chemical treatment approach, both um, aim to use CO2 gas, you can see that we achieved 40 megapascal for the compressive strength in the chemical approach. The slump flow was something similar to self-compacting concrete, and the permeability test is still awaiting to be done, most probably after this COVID-19, when the universities turn back to normal. Is it a financially viable approach to use recycled aggregate and this CO2 concrete? And it's a question that is needed. Actually, the answer to this question is needed for proper commercialization. And we need to know whether these techniques are financially viable for the contractors, the end user of these technologies. So first of all, the recycled aggregate as of 2000, actually 2 months ago, the last time I got the price for a ton of recycled aggregate, that was $20 per ton, while its natural aggregate, the blue metal, is sold for more than $100 per ton. So a simple comparison shows that like actually 80% savings for the supply of aggregate. And also the fact is that the government agencies are pushing tax deduction for green buildings as well, which means that in the future, we most probably can see that apart from the savings from the supply of recycled aggregate, government incentives will also encourage the use of environmental materials as such. Um, for the future plan, we are planning to um, design a chemical reactor for that chemical substance. As mentioned, the reactor compromises a high safety risk for the manufacturer if the process is to be handled manually. That was a highly basic material, remember that. In the future, we need to make the whole process automated with the minimum human interaction. Um, was the presentation for today. I think that I'm done with the content. I have to deliver and a special thanks to my colleague, Mrs. Kamani Jagendran, who had helped me a lot in data collection, and to the Institute of Construction Materials to provide the fundings for this research and the support that they gave. And of course, you who gave me your time to listen to these topics. So if you have any questions now, we can come up and have a chat before the next session starts at 11. Any questions, anybody?
Yes, hi Farad, how are you?
Hey, how are you?
I'm good, thank you very much. I'm just would like to ask about the experiment.
Yes.
So, yeah, is it under process or
The
um,
preliminary studies are
completed.
done.
Sorry.
The initial studies, the first preliminary experiments are done, but the university is closed now. I'm not sure what is happening in La Trobe, or if the laboratories are open or not, but the access to laboratories are highly restricted now, and
Correct. Yeah.
that's why we couldn't run the experiments. But yeah, we're trying to design a chemical reactor first, and then further on investigate. So we need some sensors in that chemical reactor to take records of what is happening inside the channel, like the pressure drop, the temperature rise. Need to quantify them to be 100% sure that what would be the optimized mixed portion of that chemical substance.
Okay. Thank you. And in terms of the cost, do you have any idea about the cost?
For the new chemical admixture, is it
Yeah.
what you're not sure about the cost yet, but definitely if we want to push it to the commercialization scale, to commercialize the scale, we have to consider a competitive price for this substance, especially in the beginning.
Yeah. Correct. All right. Thank you.
Yeah, oh, much appreciated. Okay. Um, Mr. Kandiri or Kanmani, if you have any questions, I'll be more than happy to answer. If you have any other things to contribute, you'll be also welcome. If not, I think we have to say goodbye and then wait for the next session, which starts at 11 by Noor Hazay from Bond University in Queensland. She's going to discuss the digital innovation within the construction industry. That's another interesting topic, and I'm pretty sure you can get a lot out of that as well. So yeah, it looks like that there are no questions. But again, thanks for listening and much appreciated. See you. Oh no, Hala has something to say.
Yeah. I just would like to thank you for the presentation. It was really good and was a great topic. Thank you and see you in the next session.
Much appreciated. Kanmani, I think you have something to say. Oh, maybe not. All right. Everyone have a good day. See you in the next sessions, everybody. Bye bye.